So starting tonight, we're going to wrap up our discussion on, or start to wrap up our discussion on isomerism and in coordination chemistry, and then talk a little bit about coordination number. Remember, we've been looking at this flow chart the entire time. The central question that we've been asking is that we've got two molecules with the exact same formulas, chemical formulas. Now the question that we're asking, are the bonds between the atoms in both formulas the same? If not, then we have a structure or a constitutional isomer, and we've already discussed those in detail. Now on the other side, if the bonds between the atoms are the same, that means that they're stereo or configurational isomers. Now if you take and draw the mirror image of a molecule and you can't overlap it, you know, the mirror image is not identical to the original compound, then it's a chiral isomer. So let's return to looking at our generic coordination compound Ma2B2C2. If you notice in the figure here, the two A's are cis to one another, the two B's are cis to one another, and the two C's are also cis to one another. When all three are cis to one another like that in any coordination compound, that means it is a chiral compound. So if we look at this compound right here, we have two amines that are cis to one another. That means they're 90 degrees from one another in the compound. We have two cyanos that are 90 degrees from one another. And we also have two aqua groups that are also 90 degrees from one another. So we have to, when we name this, denote that each ligand is cis to one another. So the base of this, the name for this ion is cis-diamine, cis-diaqua, cis-dicyano-cobalt-3. And it's an ion. And since its mirror image is not superimposable when you draw it out, we have to use this RS nomenclature. Just to remind you, you've seen this in organic chemistry already. Chiral isomers, by definition, a molecule or an ion and its mirror image do not have superimposable mirror images. So, for example, if you take your two hands look identical, but when you try to overlap them, like I'm doing here, notice I can't match them up. If I orient them both palm out, I can't twist my arms so that they'll lie on top of one another. Chirality is handedness. There are some common geometries that are always that display chiral compounds often. Tetrahedral complexes with 4 different ligands are always chiral. Octahedral complexes with chelating agents that have specific configurations are always chiral. Octahedral complexes with 3 to 6 different monodentate ligands, or some combination with bidentate ligands, always chiral. Or there's the possibility that they can be chiral. Now, if you remember, a pair of chiral isomers are known as enantiomers. Just to remind you a little bit about the nomenclature that goes along with chiral isomers. When I named the cobalt compound earlier, I put this R/S out in front, and that tells us about the handedness of the compound. So R, the Latin root, if I remember correctly, for R is rectus. I believe it's Latin. That means it's right-handed, so it will rotate plane polarized light towards the right. Let me back up. R means right-handed, S means left-handed. I'll get to the plane polarized light. I was thinking a little bit ahead. So R rectus right-handed, S sinister left-handed. Now the chiral compounds also can have the ability to rotate wavelength, a specific wavelength of polarized light, either clockwise or counterclockwise. And if you know which way this light is rotated, you can also give the compound the DL nomenclature at the beginning. D means dextrorotatory, that means rotating light to the right, and L means levorotatory, which is rotating light to the left. Now there's actually a third type of nomenclature that you can apply to chiral isomers. When you have chelating agents, remember chelating agents bond to the central metal cation in at least 2 places and even more, because they're larger molecules with multiple atoms that can bind to the central metal atom or central metal cation. Chelating agents can have different orientations in coordination compounds that can lead to the formation of chiral compound or chiral pairs. This is the nomenclature that you will see in the literature for chiral isomers that are chiral due to the fact that they have chelating agents. So the delta means that that there is a clockwise orientation of the chiral compound of the chelating agent, and the lambda means that there's a counterclockwise. So what you're looking at here is the metal cation, and I'm just putting in there as let's say that this is ethylene diamine. So the 2 nitrogens are bound to the metal cation, and what happens is that they're both coming out towards you in this figure. Now the carbons are still coming out, but if it looks like that the ligand is going in a clockwise fashion. So notice that the way I'm pointing the triangular wedges makes it look like that it's going clockwise. This is the delta isomer. On the other side, if it looks like that the carbons are pointing the exact opposite way, such as I'm showing here, this is known as the lambda isomer.